Hello everybody. Today I will be presenting my third milestone review. My name is Mohammad Rehan Siddiqui and I am talking about my PhD topic, minimizing motion sickness in autonomous vehicles. My supervisors are Dr. Hormoz, Dr. Pavel, and Dr. Reza. So since this is my final presentation of my PhD, I will be taking you through the journey of my 3 years, starting where the problem definition, the literature review, all the way to my research aim, strategy, questions, and then my results from the first, second, and third year. And hopefully also at the end, I will be touching on the experimental verification and discussing with you the project timeline. Starting with the problem definition, level of automation of cars is increasing day to day, and this is what exactly is the point of address at my PhD study as well. In particularly, we're looking at level 4 vehicles where the cars are officially driverless in certain environments. These self-driving cars of the future are having envisaged scenarios of future cars where people are seen to be working on their laptops, mobile phones, maybe also be allowed to swerve around, talk to other people at the back seat. And so basically what that means is that you will have high levels of non-driving passenger activities. Research in 2019 done by Monica indicates that that level of task in autonomous vehicles will generally increase the amount of motion sickness. So the major problem that we come to understand from this, from my study, is that motion sickness acts as a barrier to bring autonomous vehicles into society. Going ahead, I started then the literature review where it was important to understand what motion sickness is. And motion sickness is nothing else but a sensory conflict between the organs of balance, like vestibular, visual, and perceptives. When they conflict, they basically give you out symptoms of motion sickness, such as imbalance, dizziness, and obviously the end result being vomiting. To best describe this in land autonomous vehicles, best example would be to have the example of the army soldiers who sit at the back of the army truck, and they're basically covered up from all areas, so their visual perception is completely obscured. Because of that obscuration, when the part starts moving around or the vehicle starts moving around, they have a sensory conflict and obviously are induced to high levels of motion sickness. On the other hand, the driver who's sitting and driving, he has all his sensory organs of balance in contact, and he's visibly able to see vestibulars are working fine. So his conflict is much smaller compared to the army officer sitting at the back, resulting into having very low levels of motion sickness. So the passengers who are sitting at the back are very similar to the passengers of autonomous vehicle. So from here, we know that if the part does move around, if the vehicle does go on a path of motion, we are subject to having motion sickness for passengers. And so it was time to look and see what maneuvers are causing this motion sickness. One of the key maneuvers was identified by Griffin in his work as the cornering maneuver. In terms of frequency, it was noted that the frequency occurring at 0.16 hertz, generally between the low range of spectrum of frequency between zero point 0.1 and zero point 0.2, is lethal in terms of motion sickness. Going ahead, Jinzhou, in his paper in 2014, was able to find these comfort thresholds for the cornering maneuver. And he found out that 1.8 to 3.6 is best for comfort. Anything beyond this would go into medium or worst comfort. For other than this, the phase between lateral acceleration and roll was also an important factor. If there is no phase difference between them, and that would lead into higher motion sickness in passengers. So coming to understand this, the research gap was quite simple. There was a lot deliberated in the literature about what causes motion sickness, what are the factors of land vehicles causing motion sickness. However, there was no such practical solution or a problem solving strategy. So based on that, I developed a aim and a strategy. And the aim of my research was to limit motion sickness in self-driving cars. Now, in order to limit that, we had to design new parts that would actually limit motion sickness. So the part tracker controller, which we had from our previous works, was to be used and basically ran on these parts to make sure that our vehicle will have least amount of motion sickness. The vehicle model would then be having a lot of different objectives from which we can actually extract them and then put them into a controller such as these fuzzy logic, model predictive, and PID controllers, and can get a corrective steering angle that would actually limit motion sickness in this journey by generating a corrective steering angle. So, in a nutshell, the strategy was very simple, and that was to apply path planning of transition curves and further on using these objectives coming from the vehicle model to develop a novel cost function to limit motion sickness. Based on this, the research questions were formed. The research questions were five. The first one was, what are the major vehicle dynamic parameters in terms of motion sickness? Question two was, how path planning tools such as transition curves influence motion sickness, specifically in self-driving cars. What is the role of postural instability in causation of motion sickness, and how do route and vehicle dynamic parameters impact the passenger's postural instability? Question 4, where I had to define some major objective functions that would actually be able to develop a cost function to allow us to measure motion sickness and then further on accommodate it in real time. And last thing, what are all the other maneuvers like single lane change and double lane change maneuvers, which also have precipitations of lateral acceleration in them to contribution towards motion sickness, and how can they be resolved? So starting off with, I started looking at those thresholds and started looking to answer my question one. My objective was identify those thresholds of motion sickness in terms of vehicle dynamics. Methodology was to identify those thresholds and then design the worst path, so that the worst path would be basically transgressing all those motion sickness thresholds. The motion sickness thresholds that were defined were cornering maneuver, lateral acceleration, if happened to be above 3.6, would cause motion sickness, having consecutive and opposing directions of turns. The frequency response, obviously between zero point 0.1, zero point 0.2, and specifically at that value of 0.16 should be peaking. Steering inputs will be as abrupt as possible and will cause a lot of problem for the handling comfort. The roll and lateral motions should be also in phase. So based on that, I basically went on and designed the worst path. The worst path was made up of multiple consecutive turns, and then when passed into our path tracking controller, it was basically producing abrupt lateral accelerations. It produced roll and lateral accelerations in phase and had very high magnitudes at the low frequency, specifically peaking at that 0.16 hertz. So further on, it was now time to start the investigation and look at research question 2. The objective here was using those thresholds of motion sickness. Can we actually have path planning or ergonomic path planning done on that worst path and actually investigate and see will it reduce motion sickness? The answer or the methodology to be used was fairly easy and simple, was to use different transition curves like Hermite, Bezier, B-spline with configurations of 3-point, 4-point, and 5-point. And then see, based on our path tracking controller and motion sickness thresholds, if they do actually help us limit motion sickness. The answer to that question was, it was definitely, answer was yes, because the ergonomic paths were able to limit motion sickness. And the best path out of all those transition curves was seen to be the 3-point B-spline curve. It was not only reducing the lateral accelerations, but it was also reducing the frequency response. And it did far better than 4-point and 5-point curve configurations. So in a nutshell, 3-point B spline was doing far better. But however, there was one of the factors which was basically the phase between the roll and the lateral acceleration, which was seen to be completely in phase. In order to make sure that we investigated this part of it a bit further, we had to go into further extending our study of the ergonomic path planning. And that what we did was basically we went for the quintessential path to further answer the research question too. And this time, because we haven't got a result for the fourth or the fifth motion sickness result, our investigation was about the local control and the uniformity of these splines. Now, in order to have local control uniformity, we have to have a certain methodology. And that methodology was that we already know we have 3-point B splines doing very well. But then we want non-uniform rational B-spline curves. Now, these NURBs, they allow us to do local control, which is basically allow you to select the mid-weightage weightage at the midpoint selection. And they also allow us uniformity. So they allow us to design knot vectors such as in configurations of open, uniform, and non-uniform. And again, we will base our results on the bar tracker and then the thresholds and the cost function, which would be later on developed as a measuring tool. So looking at this, it was seen that the NURBs would actually be able to provide us a slightly better performance. By selecting the mid-weightage point at 0.75, we could see that the radius was now going beyond the 77 meters. And so we were able to reduce or keep the lateral acceleration during the turn less than 3.6 meters per second squared. Additionally, it was seen that the open uniform nectar of configuration 000-111 would by far produce the best result. Based on this, the quintessential path was now formed, which is the 3-point B NURBs. Going further on, we wanted to also investigate the research question 3, which was postural instability. So in order to understand postural instability's impact on motion sickness, we had to identify the thresholds and then design a model to relate it to motion sickness. So the methodology was do literature review, find those thresholds, find those postures, find mathematical models that will actually be that will actually be induced into our simulation, and then see the impact of the ergonomic path planning, and obviously base the results on the motion sickness thresholds. So we were able to design this strategy of motion sickness and postural instability. And the strategy was very simple. It was we would produce lateral accelerations from the bar tracking controller or the vehicle model we had. We will input this into the Sarushi Neuro network model, which she developed in 2020. And we would produce the passenger's head tilt angle or the roll angles. These angular rates of the head roll or head tilt strategy of the passenger would then be input together with the lateral acceleration of the path to produce motion sickness incidence based on the Kamaji model in 2007, which is based on subjective vertical conflict. So now once we had defined the postural instability and in terms of motion sickness, we had to now look at question 4 of our research, and that was to design that cost function or a measuring tool in order to measure as a scalar quantity motion sickness. And for that, we were looking at different objectives and see what all is the standards that are being used in research all those years that actually identify motion sickness as motion sickness. Going further, it was seen that we had already worked on designing those thresholds. So the research question 1 and 3 was very important in defining those, let's say, couple of those motion sickness objectives. Other than that, we had to also see if that cost function would actually show the real value of our investigation done in research question 2. And then obviously we have to further take this tool of cost function of the motion sickness to find a control strategy based on it. So the cost function was then formed, and it was formed based on some really good standards that are used across the literature for specifically for the handling comfort, for postural stability, and for reducing motion sickness. One of these objectives of number one was the FFT of the spectrum of the steering angle, and we were taking the RMS value of it in order to reduce or increase the handling comfort. Objective two was the frequency weighted lateral acceleration, which we call as the motion sickness dosage value. So all the lateral accelerations that fall between the range of motion sickness frequency, which is between zero point 0.1 and zero point 0.2, are only taken, which is why it is very well known to use this standard. The other thing was to look at the RMS value of the lateral part tracking error. So we want to see that how far our part tracker is tracking these parts, because the more you follow the part, the least amount of motion sickness will be seen. And so that was a very important factor as well. Objective four is the previous slide that we looked at for postural instability, which is motion sickness incidence. So this cost function was obviously then given certain weights. Each objective was given those weights based on using multiple regression analysis. Now we wanted to test our measuring tool, the cost function, and we measured it accordingly to the NURBS 3-point and the B-spline 3-point. So you can see we used three different trackers for both the curves. We use model predictive control, slide mode control, and slide mode control modified. And the same we use for B-spline. And you can see from here quite easily that NURBS was by far doing much better than the B-spline curve. Additionally, we also verified our measuring tool, this cost function. The worst path was giving the highest indicator value. It means that our cost function was able to measure on these journeys, on these paths, the motion sickness. So from here, we got to see the motion sickness cost function. We got to see that NURBS 3-point with specifically the part tracking controller, slide mode controller, since it was curvature dependent controller, was able to best be used as the quintessential path and as the part tracking controller. Going ahead, now we had the cost function. It was time to build a control strategy around this particular cost function. And the idea was use those objectives and then define that control strategy that could minimize motion sickness in real time. The methodology was use those objectives that we define in the cost function. Additionally, look at other objectives if we can have extra, inputs from them and try to reduce it more. So the idea was to look at lateral jerk, acceptable jerk value, illness rating, and then use this against modern predictive controllers like model predictive controller, fuzzy logic, PID. And we were not trying to make a standalone control strategy. We were trying to make a hybrid control strategy, which was using the slide mode controller as the path tracking controller, and it was using our obviously the motion sickness cost function and our vehicle model, and additionally it was using the NURBS 3-point curve. So this was a hybrid strategy, not just working on its own. So going ahead, when we were forming this control strategy, we named it motion sickness hybrid control strategy, and we had certain results produced based on the PID and MPC. The fuzzy logic unfortunately did not produce conclusive results, and so it's not being shown here, but the PID did. And the best two objective functions that were seen in terms of reducing motion sickness for PID were the lateral acceleration and the illness rating, and for the MPC it was the lateral acceleration. Hence, we then formed one control strategy based on these three objectives, as you can see here. And they were producing, when added all up together, a single corrective steering angle for motion sickness. So how the hybrid system would work would be that this is the slide mode controller. We would take the lateral acceleration from the vehicle model, and then we will infuse this negative feedback of the steering angle to the motion sickness, to the slide mode controller, to correct it in order to make sure that it follows the track to its best knowledge. And when we tested our motion sickness hybrid control strategy compared to the NURBS, we saw that there was a 0.4% improvement. So that meant that the hybrid control strategy, when cornering, would in real time do slightly better than the NURBS only. Going forward, we had now to look at the question number 5, because we were looking at single lane change and double lane change for the reason that we wanted to look at other maneuvers that also produce lateral movement in vehicles. And what better than single lane change and double lane change? And obviously, we already had looked at cornering. So the idea here was to formulate a single algorithm that would cater single lane change, double lane change, and cornering for minimizing motion sickness. And for that, we used a methodology of three phases. Phase one, particle sum optimization, to take the best coordinates to conduct that maneuver. Phase two, to apply the motion sickness free block, which is remove any of those parts that are actually transgressing the motion sickness threshold. Phase three was a simple trigonometric setup that would make the steering angles as comfortable and gentle as possible by making the starting and ending as symmetric as much as possible. Going forward, the motion sickness algorithm results, since it was having single lane change, double lane change, and cornering all together in one algorithm, that's why we called it the ultimate motion sickness mitigating algorithm, and in short, UMSA. So comparing the single lane change against the algorithm presented in reference 12, sine x function, we can see our motion sickness thresholds are reduced abundantly. Even for the double lane change, it can be seen quite visibly that our path for the algorithm is doing much better compared to the x sine function. Comparatively, if you look at the illness rating, our algorithms maneuvers like single lane change, double, and cornering all are performing well below the level of illness rating, indicating very or almost no sickness at all felt by the passenger in these paths. So going ahead, this basically signified that I had completely answered all my research questions. And now it was time to basically validate or verify these findings. And that was done using the RC experimental verification. This experiment was used to validate the findings of my previous results of investigation of the ergonomic parts, the motion sickness cost function, and obviously the cornering maneuver strategies and the algorithm. And we used for this experiment the RC car, which is a 1:7 scaled car with the My Rio, which is a National Instruments device for measuring all these vehicle parameters that would give us the motion sickness results. And lastly, the lab view environment with the Wi-Fi dongle was used in order to make the vehicle run autonomously on those parts. The hypothesis of this experiment were four, and each one of them was the ultimate motion sickness algorithm in terms of single lane change, double lane change, and cornering maneuver does better and reduces more motion sickness results than the standard sine x functions or standard cornering maneuvers. In general, in addition to that, the fourth hypothesis was a comparison between our own solutions, which was the hybrid control strategy. Now we had seen in the previous slide did slightly better in reducing motion sickness thresholds than ultimate motion sickness algorithm alone. And so we had to work out this experiment to make sure we would validate our findings. Before we could do that, we had to obviously calibrate the vehicle in terms of its steering angle using the Ackermann condition. And we had to also basically program the electronic speed controller of the Traxxas, which was the Castle Mamba Monster Extreme. And it was obviously had to be unlocked first and then programmed based on the database, based on these ratios that were given to us in the manual of the Traxxas. And we were able to calibrate the speed in terms of duty cycle and also the steering angle. Once this was ready, it was time for the physical parameters test. So we started testing the vehicle physically, as you can see here, with a gyro sensor, and we started taking all the physical parameters of the RC car, which is seen on the left table over here. We took its mass, we took its center of mass, we took its length, we took the stiffness of the tires. Once that was done, then in order to generate the steering angles for the parts, we had to make a full-size hypothetical model of this RC car. And for that, we applied dimension analysis, the equations you see here. And based on this, we got to see that our hypothetical real life car size model was having this mass and these values of stiffness and center of mass. And based on reference 13 and 14, we then finally validated our full size vehicle model to be equivalent to the 1998's Toyota Corolla or sedan of Toyota Corolla of 1998. And in order, because this was a passenger car, we had to obviously make a small tweak to our RC car and shift its center of mass from the center or from the rear axle towards a bit towards the front axle by adding an 800 grams of weight to it. So once this was added, the sampling rate was also fixed, and it was seen that the simulation would have a sampling of 2 times greater to the RC car. So now going ahead and trying the experimental results on those parts to validate our hypothesis. The first thing was to validate the single lane change and double lane change, and then the cornering maneuver. And the sampling rates, as I said, for the RC car was supposed to be half of the simulation, and so that's why they were fixed to that limit. If you can see closely here, the results of the single lane change can be seen. The solid line over here in the black indicates our UMSA single lane change, and the sin X is the red function, which is, as you can see, very high compared to this UMSA. And additionally, we will also see that the sin X, which is the double lane change, is in green, and compared to it, our UMSA was performing much better. And in terms of motion sickness thresholds, all of these were also shown to reduce up to 50 to 60% reduction. So that meant that the hypothesis 1 and 2 were definitely proven. Going to hypothesis 3, we had to look at the cornering maneuver, and we looked at the general turn. As you can see, is very abrupt, very high compared to our UMSA, which is the black line. And even if you look at the motion sickness thresholds, we were able to reduce up to 60 to 80% of reduction in those motion sickness thresholds. Now, comparing the motion sickness hybrid control strategy with the UMSA, which is the fourth hypothesis, it was a bit more tricky, but however, we did the cost function analysis, and we saw that the motion sickness hybrid control strategy did perform slightly better in terms of cornering against the UMSA by just 14.64%. In our simulation, we got it equal to 10.9%. So that meant that all our 4 hypotheses stand at the beginning of the experiment were definitely proven correct. Further on, we went to make some accuracy and reliability tests for the RC car experiment. Was the experiment that we conducted reliable and accurate? For that, we tested it on very high levels of speeds, such as 80 kilometers per hour in the simulation, equivalent to 21.33 in the RC car, and the same thing for the turning left maneuver. So the results can be seen here. This is what we expected. We had the experiment, obviously, is sampled half compared to the simulation, and even the motion sickness thresholds were lying in the results of accuracy of 82 to 85 and 98 to 99 in terms of the head roll angles. Furthermore, for the turning left, we had also done the same test, and we saw the sampling again was half of the sampled rate of the simulation car. So it means that the real car would go and take 9,000 milliseconds, as for our RC car would take just exactly half the time of that, which is 4,500. And again, when we compared the motion sickness threshold, it was seen that we were 85 to 88% accurate, with RMS head roll angles coming to 85 to 86% accuracy. Furthermore, we did some reliability tests by testing the vehicle under wet conditions and dry conditions. With the same maneuver, the worst part turning left, but at 2 different speeds to check the sensitivity. And we saw that, yes, definitely the system was very much sensitive. As we can see, in the wet condition, we had lower lateral acceleration as compared to the dry condition, indicating that not only our system was accurate, but a lot reliable as well. Further to my project, this is the project timeline. This is what I have done in all my journey from 3 years. So starting from year 2, 3 to 4, now I'm working on basically presenting this work of my experiment, which is my final basic publication for a book chapter, and hopefully also I've been accepted for a conference for that. Additionally, I'm working on a narrative review paper for Elsevier, which will be having all the discussions that you saw here today in that one particular paper, which is a Q1 journal. Additionally, we believe that there is a lot of scope with this autonomous vehicle being implemented today in my research, and we will look for a grant proposal for the Defense Innovation Hub. And obviously, I will be in the first quarter of my year 4 completing my work in thesis. So going to the list of publications, this is the amount of work that I have done in terms of publications. You can see I have 2 published works, and the third one is on the way. It's been already accepted by one of the viewers. We're just waiting for the other two to say yes to it as well. And then the review, a narrative review paper, which is my final work for this particular project. For conferences, I've been to two, and I will be going to the third one in the end of November. And I have already published one book chapter, and I am publishing the last experimental chapter as a book chapter as well. It's been accepted, but will be published hopefully by next year. Coming to my references, these are just a few of the references that I've worked with. I've worked with mostly around 300 plus references, but however, in terms of the presentation today, the few new references that I added for my work in, let's say, the experimental work were references 12, 13, and 14. And so we come to the end of my presentation. So that was my journey of 3 years of my PhD in more or so 30, 31 minutes. And I hope you enjoyed every bit of it. And I hope that I explained it very well so that you don't have any questions remaining. But if you do, you're most welcome to ask me. Thank you so much for attending this milestone review. Thank you.